All right, in this part of our course, we will talk about the exponential distribution. The exponential distribution is going to be very important when we talk about the Poisson process. So I know all of you already know about the exponential random variable, so we can treat this as really a review and maybe look into sort of interesting properties of the distribution. So let's remind ourselves, random variable x is said to be exponential with some rate lambda if the probability density function of the random variable x is given by this, lambda times e to the minus lambda x for positive values of x and 0 otherwise. So the distribution has only one parameter which it's controlled by. It's this parameter lambda, it's the rate. It controls the rate of drop, really, of the values. So let's just draw two possible values. For example, suppose lambda is equal to 2. This will start at 2 and decay to 0. Or suppose lambda is equal to maybe 0.5. It will decay to 0 like this. But this is not correct because they should cross, right? How do you know that they should cross? Well, because the area under them will have to integrate to 1. So we cannot have one curve always above the other, obviously. So, yeah, as you can see, I mean, my drawing is not exact. There's an exact drawing in the lecture notes, but the one with the larger lambda is going to decay faster. Lambda equals 2, lambda equals 0.5. I suggest you also try drawing some of these curves in your computer and see how they look. Now, what I particularly remember about the exponential distribution is not this PDF per se, but it's complementary CDF. What is the complementary CDF? The probability that x is larger than x. In other words, 1 minus the cumulative distribution function. How do we compute that? Easy. By integration from x to infinity, integrate the density. And this is a super easy integral. And the result that we're going to get is what? E to the minus lambda x for x bigger than or equal to 0. All right. So then this is a perfect exponential decay. So in the case of a exponential random variable with parameter lambda, the probability that x exceeds a certain value decays exponentially in that value. What is the value here? Exactly. The probability that it is positive, in other words, probability that it's non-negative is 1. And the probability that it exceeds, this does not touch 0 here. Sorry for my imperfect drawing. It's not going to, of course, touch 0. It's going to decay to 0. Okay. And that creates a lot of magical properties. The first magical property is the memorylessness property. An exponential random variable is the only continuous memoryless distribution. What does that mean? Consider the probability that x is bigger than some let's say t plus x, given that it's already known to be bigger than t. The probability that x is bigger than t plus x, given that it's already bigger than t. How do we compute this? Let's use the definition of conditional probabilities. This can be written as the probability that x is bigger than t plus x and x is bigger than t divided by what? Shall we close that door maybe? Thank you. But maybe it's too late. So what is the probability that x is bigger than t plus x and x is bigger than t? By the way, of course, we're talking about a positive t and a positive x, right? Given that x is already bigger than t, like, no, not given. What is the probability that x is bigger than this value and x is also bigger than this value? Well, if it is bigger than this value, this is automatically satisfied. So this is the probability that x is bigger than t plus x. But then we already know for the exponential, the probability of being larger than t plus x is e to the minus what? Lambda t plus x. And the denominator is e to the minus lambda t. So the ratio is e to the minus lambda x. What does that mean? It means that given it's already bigger than t, the probability that it's bigger than x more than t is the same as probability of being more than x in the first place. So if you're waiting for the bus and bus arrivals are distributed according to exponential random variables, given that you already waited for t units of time, what is the probability you'll wait for x more units of time? It doesn't really matter if this says how much you waited. It's like going to the bus stop and waiting from in the first place. So this is basically, this is why it's called the memorylessness property. The past does not matter. Right, okay. So returning to the example with the bus. Suppose you go to the bus stop and basically wait there. This is the bus stop. And you will leave whenever at t equal to 0 you go to the bus stop and you look at the schedule. The schedule says bus arrivals, inter-arrival times have mean 10 minutes. Okay. Now the schedule can be very strict. Like buses are separated by exactly 10 minutes. Or the schedule could be random, such that the expected time between buses is random and exponentially distributed. So let's say deterministic, x equals 10, or random, x is exponential with mean 10. Parameter what? What is the parameter if the mean is going to be 10? The expectation of a random variable, exponential random variable with rate lambda is 1 over lambda. So this should be 1 over 10. Exponential with parameter 1 over 10, such that the expectation of x is 10 minutes. Which one would you prefer? Okay, it depends, right? So let's compute the probability that my weight is going to be more than x, given that I already waited for t minutes. Let's not say t. I already waited for y minutes. Okay? Now, in the deterministic case, if I waited for y minutes, my remaining amount of weight, if y is between 0 and 10, my remaining amount of weight, w, is 10 minus y. And I will never wait for more than 10 minutes. My waiting time is going to be between 0 and 10. That's it. But in the exponential case, what is the probability that I wait more than x minutes, given that I already waited y minutes? Well, that probability is going to be e to the minus what? Right, lambda is 1, so y over 10. So what is the expected value of my weight then? The expectation related to an exponential with mean 10. That's 10. So basically, when the bus arrivals are random, I can wait from 0 up to infinity. There's no, strictly speaking, my waiting time is not guaranteed to be below a certain value. Of course, it's going to be finite with probability 1, but it's not guaranteed to be below 10 or below 20 even, right? And its expectation is always equal to 10 and doesn't matter how much I've waited so far. So which one would you prefer? Many people would prefer this. Some people may prefer this because you can get lucky, right? With this, you know that if you just saw the bus leaving, when you run to the stop and see the bus leaving, you know that you're there for 10 minutes. Here, you can get lucky. The next bus inter-arrival time can be 1 minute. So, okay. So, this memorylessness property is going to lead to a lot of interesting things in the Poisson process that we will study in further lectures, which is dealt with a lot in communication systems and networks, and queuing systems, and many other places. So let's talk about the case of racing exponentials. Suppose we have two exponential random variables with the same parameter or different parameters. Okay? And we are interested in the minimum. Okay? What is the distribution of the minimum? Okay? So let x1, x2, xk be independent and exponential with parameter lambda. Okay, they are IID exponential with parameter lambda. Let y be the minimum of x1 up to xk. What is the distribution of y? This is going to be handled easiest when we write again the complementary distribution function of y. The probability that y is larger than some value, small x, is equal to the probability, well, for the minimum to be larger than x, all of the individual xi's must be larger, right? So x1 must be larger than x, x2 must be larger than x, xk must be larger than x. But then these random variables are independent, so we can multiply the probabilities. But then each of these probabilities is equal to what? E to the minus lambda x. So we have e to the minus k lambda x because we're multiplying k of these. But what does this tell me? The complementary distribution function is that of an exponential at the rate k times lambda. And the complementary distribution function uniquely determines a distribution. It's the same as knowing the density because I can differentiate this, multiply by -1 and find the density. So this is then exponential with rate k times lambda. In general, if x1 is exponential with parameter lambda 1, x2 is exponential with parameter lambda 2, then the minimum of x1 and x2 is exponential with parameter what? By this argument, by the sum, lambda 1 plus lambda 2. So when two exponentials race, the winner is an exponential with rate being the sum of the two rates. Let's apply this to a queuing scenario at a service facility. So suppose you go to the bank and there are two tellers. Consider two desks. And when you arrive, both tellers are busy currently. You arrive. And then somebody else arrives behind you, so you will get queued. You have two strategies. Either both of you can wait here and then go to the teller that is going to get freed up next, or you can choose your queue a priori, choose your queue beforehand, and you, for example, pick this one, wait here, and the other person joins this one. Which one is better? So the question is, wait for both tellers, join the first one that gets free, or join a random queue. Or pick a teller at random. This is teller 1, teller 2. would you pick a teller at random, or would you wait and join the one that is? And this is really something that is an issue today, even as we speak. At a lot of service facilities, think of supermarkets, for example. Think of a busy supermarket at rush hour. All the cashiers are busy. What do? What is your strategy? You have to pick one of the cashiers. It's not like everybody gets queued up and then the person at the head of the queue is allowed to get to the first cashier that becomes idle. That is done in a lot of stores, but not at supermarkets, right? At least not in the ones that I recall recently. Okay, so which strategy is better for the person who's coming in? The first one, that's pretty obvious, right? Because here you get to observe what's going to happen, right? And then choose. Here you may not be lucky. Okay, in this case, the person who joined after you may get service before you. Okay, so let's compute. Let's compute what? First of all, suppose this one has a service time x1 that is exponential with rate lambda 1. And this has a service time which is exponential with rate lambda 2. Okay? So in this case, let's compute part A. Pick a teller at random. Pick a teller at random. Okay. What is the expected waiting time? That is, you pick a teller at random and then you wait until the service at that teller gets completed. The customer that's being served leaves. Okay, what is the expected waiting time? This is the, well, suppose you pick them with equal probability. You may also pick them with different probabilities. Let's focus on the case that you pick them equally likely at random. So with probability 1/2, you selected the first teller, and the expected waiting time is let's just say expectation of x1. And with probability 1/2, you pick the other one. The expected waiting time is the expectation of x2. Well, that is 1 over lambda 1. So this is 2 over lambda 1. I'm sorry, 1 over 2 lambda 1, 1 over 2 lambda 2. If you want, let's write it in terms of lambda 1 plus lambda 2 over 2 lambda 1 lambda 2. Let's apply the second strategy. The answer to that you already know from racing exponentials. In the second strategy, your waiting time is what? It's the minimum of x1 and x2. So the expected waiting time, well, you already know that the minimum x1 and x2 is exponential. It's the winner of the race between two exponentials, and its rate is lambda 1 plus lambda 2. So then the expected waiting time is what? 1 over lambda 1 plus lambda 2. Aha. So which one is better? So let's, for example, suppose lambda 1 was equal to lambda 2. Let's call it lambda. This would be part A. The answer to part A would be 2 lambda over 2 lambda squared. No, 2 lambda over 2 lambda squared, which is 1 over lambda. Which makes sense, right? Because you're picking one at random and they're equally identically distributed. How about part B, in this case? 1 over 2 lambda. 1 over lambda versus 1 over 2 lambda. So that clearly shows that the second strategy is better. Okay. And that is only one of the magical properties of the exponential distribution. Next time we will pick up on this, talk a little bit more about the exponential and then the Poisson process, which is built on the exponential distribution. So see you next time.